Hey, everyone. So I think we've waited the required 5 minutes to give a chance for any stragglers to join in. So we're going to kick off at this point and get started. So I'm Moran. Nice to meet you all, and thank you for taking the time to join us today. I am from Superwise. So if you are not familiar at this point, Superwise is a machine learning observability company. So we're mainly focused around helping data scientists and machine learning engineers stay on top of their models once they're in production, managing issues like drift, bias, performance degradation, and so forth. But that is not the topic that we are here to hear about today. We are going to be talking about search and search relevancy and how to make search relevancy better. I do want to mention, though, before we shift over into our amazing speaker, Gad, and let him introduce himself, that everything that we're talking about today will be sent over after the webinar itself. So we'll send over the recording, and we'll also send over access to all of the resources we'll discuss during the webinar itself. So there's no need to start taking screenshots or jolting things down. We'll make sure that you get it in an organized fashion once we're done. And with that, I'm going to hand things over to Gad, and he is going to take us through the world of search.
Thank you. Pleasure to be here. So as Moran said, we're going to talk today about monitoring the quality of AI-driven search. Just a bit of an intro about me. My name is Gad. I'm the founder of TensorOps and also serving as the CTO. We're a consulting company. We help machine learn. So what essentially we do is we help companies build better AI practices within their organization and reach their KPIs using AI. And this meetup, of course, is with our partners from Superwise. So today we're going to talk about search and search for industries and what is search and how companies use search. And then we're going to ask ourselves, what are good search results and how do we get there? And of course, no meetup in AI today can ignore LLMs. So we are also going to talk about the impact of LLMs on search. So we actually have a poll to kickstart. So we wanted to ask you, are you implementing search within your organization? So let's give people a few minutes. We want to know if you're implementing search within your organization. Okay, so I see here that some are not, and very little have their own algorithms. And most of the people rely here on Elasticsearch or other similar tools, which is very common to what I also see. Some actually plan to implement search within their organization. So it's very interesting. I think we have a very diverse group here. We'll try to cover everything from beginner's guide to some expert topics. So let's start with the basics, all right? What is search? So the search is an algorithm or maybe a method of retrieving information. And when we think of search, maybe we think of like Bing versus Google. It's the action of when I'm given some kind of query, when I'm looking for some document, how do I retrieve this document? And it appears that not just Google implemented search as part of their business, but you can think of Netflix, for example, right? So when you go on Netflix and you search for a movie, then they have to provide you with not just that movie, but maybe other movies that are going to be interesting for you. So they have their own search system. I don't know how many of you are buying on Amazon.com, but so I heard that some people that are going and searching on Amazon.com or want to buy something on Amazon.com, they're not actually performing the search on Amazon.com, but rather they're looking for the name of the product on Google, adding Amazon at the end. So I'm not saying it to glorify the Google search engine, but mostly to mention how important it is for a company to have a good search engine. Because if it's not, you're letting some other company maybe direct the traffic to your site. So having a good search algorithm could impact your business a lot if you're doing e-commerce. Another example that we have here at the top is legal. So it appears that legal documents, this is an example from an Israeli company. It appears that legal documents in Israel are not well indexed. So court rulings and maybe, I don't know, subpoenas and all kind of like stuff that is supposed to be public, they're not well indexed, and specifically they're in the Hebrew language. So Google doesn't index them very well as well. So there is a company that was built end to end on the ability to search legal data. And they've built their own practice on their internal search engine. So you see a lot of industries that are implementing search, and it can have from very little to a lot of impact on the business. But what are good search results? Okay, so what is a good search? So often when you talk about search, you don't talk about it in terms of good and bad. You talk about it in terms of relevance, which is a more continuous metric or continuous measurement. So let's say that I'm looking for a sushi recipe, okay? So when I'm looking for a sushi recipe, let's say that I have like a ton of documents that contain the word sushi, or not even contain the word sushi, like some tons of documents in which I want to know if these are the documents that are going to be the most relevant for my search result. So I could come with this hypothetical score that I'll call relevance, that will allow me to basically order my results according to this score, right? And then I just need to retrieve the most relevant ones, right? The ones that has the highest relevance, the highest score. So the search relevance is a key factor in search. And how do we measure this relevance? Okay, so I just came up with the idea of search relevance, but it appears to be not a very easy task to know what is a relevant search. There are basically two approaches. One is explicit. Okay, I'm going to basically go ahead and ask the user, are these good search results? Let me just grab a little bit of water. Okay, so I can ask the user, are the search results that I presented to you relevant or not? I can even do it not in search result. I can just pick a random result or random something and just ask the user, is it relevant to you? Of course, these are very, very valuable and very reliable tagging, but they're also quite expensive to collect because they requires your user to actively go and respond. The other alternative is much cheaper to collect. It's implicit, right? So you can think of again, Google as google.com is the search engine. If I'm clicking on a result, it might mean that it's relevant, but it can also mean that it's just, I did it by mistake, or maybe Google presented me with 10 options. None of them was really relevant, but these are the 10 options that I just got. So I picked one of them. It doesn't really mean that this result was actually relevant. So the problem with implicit is that it's noisy and it doesn't necessarily represent relevance. But of course, cheap to collect. So you must ask yourself, what's the right one? So again, let me speak about a company that we all know, Google, and they're doing it quite well with their map application, right? So when I'm looking for a restaurant in Google Maps, then it not only gives me a list of documents or a list of restaurants, it will also give me the matching score, like how relevant is this document, how relevant is this restaurant for me? And it's going to be based on multiple factors, right? On the location, or have I visited it before? So Google actually in Maps implements the two methods, because for once, they will see my interaction with the search results. They will see if I actually went there. So this is implicit, right? Because they can understand that if they presented me with a restaurant and I actually attended it, then maybe the search result was relevant. But also they will ping me afterwards and they're going to ask me, rate your visit. How was this restaurant for you? And this explicit tagging is also going to help them improve the search results. Now that makes me think of search as really a machine learning problem. It doesn't have to be a machine learning problem, but I can think about it as a machine learning problem. And when I'm talking about machine learning problems, I want to talk about often how I monitor them, right? So machine learning has a specific methodology on how you monitor machine learning deployments versus other deployments or like backend deployments. You don't only measure the latency or the load of the servers. This is also important to do, but you also want to measure two major things. One is the accuracy of the model. I made a prediction, and then maybe I can get a label if my prediction was correct or not. I want to continuously monitor how accurate my search results are. And this is not a regular monitoring. Like if you use standard software monitoring tools, you're probably not going to find these in these. The other thing that I want to measure, and that's actually very important in machine learning, is I want to measure the data coming in to my model. And why is that? Imagine that I train my model on maybe I'm looking for like sushi, like the previous example, like I'm looking for sushi recipe. And all the data that I trained on was related to sushi. Now somebody goes and then searches for pizza, then maybe my search results are not going to be as good, because not that my model changed or nothing is like wrong with my model, but like new data is coming in. This concept is called drift. So you can have drift in your data. It means that the data that's coming into your inference model is changed from the data that you collected during training. So in this regard, Superwise is exactly the tool for that. There are other tools for that, but specifically I like Superwise because they have a commercial version for companies and also a community edition if you are a developer who's using it for their own purposes, and if you have a limited number of models that you want to track. And Superwise basically allows you to do these two things that I just mentioned. It allows you to track the quality of the predictions, but as well, but the quality of the data coming in as well. So you can think about it like maybe I have an e-commerce website and I'm deploying my own model, and then I can measure how much of these turned into sales or what was the revenue coming from this model. And then I can go ahead and test out new models and see which model versions generated more revenues. So this is a very powerful way of looking at search as a machine learning problem. How I can implement it in terms of an architecture. So here's an example, like the user is performing some query, which can be textual. It typically is textual. It's submitting it to my application, and then I have my own internal search engine. This one returned the result, and then I'm logging the results data together with the query onto Superwise, getting back to the dashboard that I just showed. How about explicit? So in the way that we're talking about explicit data labeling, then we actually need a labeling tool. We need humans to go over this labeled data, I beg your pardon, of this search data and then label it. So just imagine one user is performing a query, and then it goes to my search engine again. I'm getting results. I'm logging everything, the search query, the search results, the click. Again, everything goes to Superwise. And then you can retrieve the data back from Superwise. And since I have a unique identifier for the search queries and the search results, I can go and put it in my labeling tool and then get user feedback saying if it's good or bad. I can also direct it back to the user and then ping them through my app to ask them to label the data for me. So this is a very interesting capability of Superwise, to be able to put after the effect labeling on data that was already logged. So the data that you put in Superwise is actually mutable, which is important for after the effect logging of events. Okay. So we spoke about search, and of course, the hottest topic these days when we're talking about machine learning and AI are LLMs. So large language models, the ones that are behind technologies like ChatGPT. So what is behind them and how do they impact search? So let's talk again about the sushi example that I gave you. So I'm looking for a sushi recipe, and this is a schematic idea of the results that I'm going to get, but I actually went on Google and searched it. And so it turns out that when I'm looking for sushi recipes, the word recipe does not appear in the results. So this is actually something that like I used on my search on my browser, and I requested for sushi recipes, and I got homemade sushi, how to make sushi. So how does Google know that homemade sushi and sushi recipes actually refer to the same concept, to the same idea? How do they know that this is relevant for sushi recipes, even though the word recipe does not appear explicitly in the document? Maybe it appears later. Definitely not in the title. And some of the ways to implement it, it's not the only way to implement it, but some of the way to implement it is using something called vector search. So the idea of vector search is based on a concept called embedding. And embedding lets me take different types of media. It can be images, it can be text, it can be audio, pass them through a network, through a neural network, and then get vectors out of them. These vectors are called embedded vectors. So I took an image and turned it into an embedded vector. I took text and I put it and I transformed it into an embedded vector. And then once I have these vectors, it appears that I can apply very simple math on top of them in order to come up with better calculations for relevance. So how can I do that? The most classic example is an algorithm from 2013 published by Google called word2vec. So word2vec was kind of like the first model that introduced the concept of embedding similarity. They found out that words with similar meanings are closer in the vectoric space. So if I apply a metric, a method called cosine similarity, which is a very basic, simple calculation of multiplying the two vectors one against another, I'm going to get a number. And the number is going to represent how much these vectors are similar. And it sort of turns out that for these embedded words, for these embedded vectors, the closer the vectors are, the closer the meaning is. And the better the models are, the better the embedding, then the stronger this correlation. So it can help me identify correlations between countries and capital cities, between verbs, between tenses, between roles, between genders. And this is extremely interesting and extremely powerful, and it's not that new. How am I going to combine the two? So I typically have my old methods of doing search, which is something like what Elasticsearch does, counting words. So let's say that this is document, like this is the first example that I have, and this is my query. My query is hello, and the document is hello world. And then I have one matched word, right? It's hello in both of them. And I can go and ask the users, what's the relevance? So I'm going to get labels here, and it can be one as relevant or not relevant. And it can also be some other metrics, like say how much the results are relevant to the query on a scale of 1 to 5. That can also be a way to measure relevance. So if I want to combine vector search together with classical search, which is based on these word matches, I can just put them as features. So I mentioned similarity, like cosine similarity. So I can embed the sentence hello and the sentence hello world, which is, this is like sentence with one word, but this is a sentence with two words. And then I can calculate the similarity between these two vectors, and I'm going to get a score. Okay. I cannot vouch for the score. It's coming from a model that is kind of like a black box, but so it turns out that if I train a model in that, and right, you already see that I have here a sample with features and a label, and then I can just train a machine learning model on top of that. And I have a predictor that can tell me, given a query and a document, what's the relevance, which is a very nice way of doing that. To understand like the impact of LLMs on search results, we kind of did a little bit of experiment on the Home Depot challenge. So let me talk about the Home Depot challenge and what it was, and then I'm going to see the impact. So the Home Depot challenge is quite of an old challenge already. 7 years ago, they published on Kaggle, which is a platform for competition, for data science competitions. Basically, companies can go put their data there, and then they let the community compete on building the best models, and then making predictions in order to try to minimize some score or maximize some score, and then climb a leaderboard. So Home Depot came with their competition 7 years ago. I think they had tens of thousands of documents, search queries and documents of items from the Home Depot website. And people had to build models in order to predict, given a query and a document, what's going to be the relevance. At that time, Word2Vec already existed. But since then, there were a lot of improvements. So we decided to go back in time and try to apply 2023 methods on the 2015 competition. And you're just going to see what we got there. Okay, so these are a list of features that we basically took and like try to see what's going to be the importance of them. So you can see here, match words between the title and the word. And when you apply Word2Vec, then you see that it's kind of like in the middle. Actual explicit word matching between the query in the title or the query in the body text was more important than Word2Vec. But when you move to a later model called BERT, which already allows you to not just do embedding of single words, but embedding of complete sentences, and it's a much bigger model, you already see it climbing up further and pushing down the importance of other features. And when you go and try to do it with the OpenAI embedding, then it really shifts down all the rest of the features. So the bigger the models are, and the more fine the embeddings get, it's more and more comfortable for models to rely on them. So models like XGBoost or LightGBM that are going to be your final ranker, mostly for these cases, they're going to be greedy. If there is a feature that is very correlated or very informative towards the target of relevance, they're just going to use it. So you can see that the better embeddings you're going to give them, the more the embeddings are going to take over in the consideration of the algorithm in what is a good search result. The reason for that, this is again from a Google blog post, and they're mentioning that the bigger the models get, language models specifically, the more capabilities they gain. Okay, this is already a year ago from Google. I think it's from Palm. And they basically noticed that once you increase the size of the model, they're capable of understanding larger and larger, like more and more concepts and more complicated concepts. So as the models became bigger, the embeddings became better. You can implement that. For example, this is from Pinecone. So Pinecone suggests combining Elasticsearch with vector search in the way that they're a vector database. They're going to be responsible for holding your data. And then you're going to get documents coming out of vector search. And then Elasticsearch is going to do the classic lexical search or term-based search that we all know. And then you take these two basically recall groups. One is more lexical and one is vector search, and you get the best out of them. How do you get the best out of them? So this is another architecture that you can maybe implement. You have a user. The user is performing a query. This is specifically on Google Cloud, but there are other ways to do that. The user performs a query, and then the query goes to an embedding model. The embedding model goes to some vector database called embedding endpoint and matching engine. You're going to get a score coming out of it. And then you still have Elasticsearch. So you're going to get the most relevant documents out of Elasticsearch and the most relevant documents out of this matching endpoint or matching engine. And then you're going to have a ranker like LightGBM deciding between them, giving back to the user the most relevant search results. So did we solve the search problem with large language models? Because we do see that they're getting much better. They are improving search results, but is it game over? Are we done yet? So of course, the answer is no. There are still a lot of limitations with large language models. Some of them are related to cost and performance, but some of them are already related to some biases. You need to remember that when you're using a large language model, you're introducing something that is kind of like a black box. It's less and less interpretable and less allows you to understand why it reached these results. One thing that you see in large language models is sometimes that when they're trained on more data coming out of a specific language or culture, then other domains may get neglected. So if you see, for example, the word Amanda and Ashley in some models, which are maybe American typical names, and you measure the distance to a burger, which is typically considered an American food, the distance will be somewhat close. But if you look at maybe an Indian name and an Oriental type of food like curry, you will see that they appear closer. What it can result in is that in some data sets, if you search for Rakesh, you might find out results coming with curry, which can lead to very racist and unpleasant behavior of your search engine. So how can you still get the benefit of using vector search from LLMs and avoid these like black boxes that you're going to experience with these models? So we are actually today announcing for the first time in public a project that Superwise have been working on called Alameda. So Alameda is an open source library. It is currently in closed beta. You are all going to get, after this meetup, link to how you can join this project. It's going to be announced officially in a few days. I'm the first one speaking about it in public probably. And what it helps you do is it helps you provide visibility and explainability to your LLM models. And how does it do it? And how Alameda does it? The idea is basically, let's go back to the traditional features that we could understood. And when we're sending data over to an LLM, let's also send it over to Alameda to do the analysis, enrich our samples, enrich our predictions, and then later on we can analyze them in these dimensions that Alameda helped us produce. So the way to work with it is quite simple. You basically create an object, and then you run it on your data set, and then Alameda automatically does for you the feature extraction. What kind of features are we talking about? So for example, it's going to measure how much emoji you have in your data. What's the language of the language of the text that you submitted? Punctuation, length, all of these metrics that later on you can just like plug them in to your inference models. Here's an example of an architecture that you can implement. So a user, again, is performing some query on your search engine, and then they're getting results. And let's imagine that these results are going to come directly from Pinecone with vector search. No feature extraction whatsoever on your end, just vector search. And it's going to be great. It's going to be good results. But on occasions, it's going to mess up, right? On occasions, the models are not going to provide you with good results. So you, again, can log your search results on Superwise. And then you can also use Alameda in order to enrich this text that was sent to the vector search, and then put them in as attributes. Okay, you can enrich basically your samples and the predictions. Once you do that, you basically are storing in Superwise the enriched versions of your predictions. And later on, somebody can go and label the data for you, or you can go and ask the users to provide you feedback, and you'll be able to analyze your predictions with these dimensions. So you can notice that you're maybe underperforming on certain languages, or when emojis appear, your models tend to perform less good. And then what you can do is maybe retrain your LLM, or refer to another LLM, or introduce biases correction, or maybe clean the data before. I personally like the idea of Alameda specifically because it's open source, and the fact that it's open source lets you kind of trust the idea that your data is not going to get abused. Many companies that like we see don't have access to the raw data. So you can think of organizations that promise their end users, we are not going to look at your data. but we still want to do machine learning for you. We still want to provide you with good user experience. So the fact that I'm only extracting metadata allows me to get visibility to why my models are performing or underperforming without actually accessing the raw data. So again, Alameda is going to be announced in a few days. You all have the opportunity to join the closed beta and to contribute to it and expand it and experiment with it and give supervised feedback. Of course, again, if I'm like logging my features and my predictions on supervised together, then I can basically later say, so on maybe title length or maybe on document length, I have different scores or different performance of my search algorithms, giving me more visibility to how my models perform. So that is it for search relevance monitoring, and also LLMs and how they impact and how we can gain visibility to what they do. That is it for me.
Cool. So thank you, Gad, for an awesome session, obviously. We're going to give Gad a chance to have some water. And in the meantime, if anyone has any questions that they want to ask, feel free to put them in the chat and we can get to them and answer them as well for you.
Don't be shy.
Normally, about half of the people end up writing emails afterwards to ask these questions regardless. I will say, though, in the close about Alameda, so we're going to be putting it out properly. Oh, yeah. So, sure. So we're going to be launching Alameda officially next week. It is open source and it is still in its infancy. Originally, the project started out within the monitoring platform proper. We simply wanted to expand our ability to support additional use cases like NLP or like vision. But as we started to work on it, we realized that there were additional potential applications for the package. But what we're doing at its core is we're looking at unstructured data and transforming it into a tabular representation. So the concept behind meta features in general, in the context of NLP, is that they're separated into two categories. You're going to have a category which is more statistical in its essence, looking at things like word count, text length, and so forth. And then there are meta features that are more contextual, things like hinted profanity, sentiment analysis, and so forth. So a lot of times when you're looking at these text kind of use cases or challenges, you need to go ahead and collect a huge variety of different libraries in order to compute them. And then afterwards, you're kind of left in the dark in regards to how everything is behaving on an ongoing fashion. So yes, I think within the use case, so the question here in the chat, because it's just sent to host and panelists instead of to everyone, is could it be used to enrich the query and documents to improve the embeddings in the embedding database? So yes, you could do that exactly in that fashion. You could essentially enrich all of these things, extract them out, and do a retraining cycle on them. So I see no reason why you couldn't. One of the use cases built in beyond monitoring is EDA. Another potential use case that we're looking at here is essentially kind of looking at modeling itself. So taking these black box models and using Alameda to extract potential features and seeing how you can recreate these results with simpler modeling architectures instead. So I think there's a lot of things today that, we've grown up in the era of deep learning and we automatically gravitate toward these type of models. But Alameda does give a window of visibility into them and an opportunity to see if we can achieve similar results with less sophisticated or resource-intensive architectures behind them. But you could definitely do all of this to improve. And I think there are probably a few use cases here popping up that we haven't thought about, which is exactly why it's going out under open source. So following this, tomorrow morning, we're going to send over the recording, and I will share also information for whoever wants to join the beta itself. And we welcome everyone, including contributors. Any more questions? Cool. So I think we are going to say adieu to everyone. Thank you all for taking the time to join us, and don't be shy. If you have questions afterwards or something pops up that you didn't think about in this moment, these are our contact information. You can reach out to us at any time, and we will also share our personal contact information in the follow-up email that will go out to everyone. So goodbye.